Okay. People come in, they'll come in. All right. How's everybody doing? Good weekend? Solid weekend? Didn't go anywhere? Stayed in your room the entire time? Good. I had an excellent weekend as well. There was a bear down the street from my apartment. So that's pretty cool. All right. So today we're going to talk about limits analytically. This is going to be how we find limits most of the time in class. It's not going to invalidate the other methods that you know for finding limits, but this is usually how we're going to take our first stab at finding limits. But don't forget, you can always, if you can't evaluate some limit that you're looking at, you can always try to make a table of values, or you could always try to plot a graph using Desmos, the app I told you all to get. And let me pull that up really quick. Here's Desmos. And it works just like you want. You can say y equals 2x plus 1. Wow, beautiful graph, Desmos. Thank you, Desmos. So that's how you use that. You can plot two graphs at once. Let's even do y squared plus x squared equals 1. Oops, forgot the x. X, there we go, squared. Perfect, wow, look at that, beautiful, it's amazing. So you can use this app. Later we're gonna talk about curve sketching and creating creating graphs just using a little bit of information that you're gonna learn over the course of the semester. But most of the time, if you need to look at a graph, using this utility is totally fine. Make use of it freely to help you estimate what a limit should be. Okay. So back to limits. All right, so you guys have homework that's due tonight by 11:59. I got some emails last night at like 11:40. It's due tonight at 11:59. So if you have any questions about that, feel free to ask me either now or during my office hours, which are, I have office hours today, 1 to 3. The Zoom room will also be open, so you can always connect to the Zoom room. And reminder, I just showed you that Desmos app. If you don't have it, it's going to be really useful for, again, estimating limits using a graph if you like to do that. Okay. So any questions on any of these announcements? Questions on homework or anything? All right, cool beans. So today we're going to be talking we're going to start off with the formal definition of a limit that I mentioned last time. And then we're going to talk about finding limits analytically. Okay, so last time I told you guys about the formal definition of a limit. And so we write that the limit as x approaches a of f of x is equal to L to mean that if somebody gives us some small number epsilon, this guy is called epsilon there, then we can find some other small positive number delta, so that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. Okay, so remember that this line here, this is just math talk for x is really close to a, but not equal to a. That's all that's saying. And similarly, this line here is just math talk for f of x is really close to L. And we could have f of x equal to L, because there's no 0 less than on the left there. Okay? So we don't care what happens when x is a, but f of x is totally allowed to be equal to L. That's totally fine. That's great. So let's use this epsilon delta definition of a limit to prove that the limit as x approaches 2 of just the constant function 6 is 6. hopefully that is clear. If you draw the graph of this, let's look at the graph. If I draw the graph, y equals 6. Well, as x approaches 2, it looks like y is approaching 6, right? This problem is a little silly, but it shows what we need, how we need to think about these problems. Okay, so whenever you're doing one of these epsilon delta proofs, you're always going to start every single time with the words let epsilon be greater than 0. Okay? That is math speak for someone walks into the room and gives me a small number. Okay? We don't have any control over epsilon. We only control delta. But given this epsilon, what do we want to do? We want to try to find x close to 2 in this instance, so that if x is close enough to 2, then f of x, which f of x is just 6 here, minus 6 is less than epsilon, right? If we can find a delta so that, find delta greater than 0, so that, let me erase this really quick, so that 0 less than x minus 2 less than delta means that f of x minus 6 is less than epsilon. That's what we need to do. Well, for this problem, this is kind of silly to even talk about, because what is f of x minus 6? It's 0. It doesn't matter what x is, right? So we can actually choose delta to be anything, and this will still hold. Anything positive. Okay? So, yeah, you guys just said that f of x, this part is always 0. So I'm just going to choose delta to be equal to 1, but you can choose delta again to be any positive number. I just love the number 1. Well, if that's the case, then we're going to take x minus 2 less than 1 implies that f of x minus 6, which is just equal to 6 minus 6, which is equal to 0, and that's always less than epsilon, right? Because epsilon is a small positive number. And so that's exactly what we wanted to do. We found delta, which is 1. You could have picked 2. You could have even picked 3. You could have picked anything positive for delta, and you would still get this line, which is the line that we need to say that this limit exists and is 6. Okay? This problem, again, is a little silly. This problem is a little silly, but yeah, it seems almost trivial because f of x minus 6 is always 0. But that's exactly what we need for this problem, okay? Are there any questions about this silly epsilon delta proof? And do you guys hopefully see that if I'm looking at the limit as x approaches any old a of a constant number, the answer is going to be the limit is a constant, right? So that's going to be important to remember later, that the limit as x approaches a for any old constant value c, well, that's just equal to c. And you can go through this exact same thing, just replace all the 6s with c's and all the 2s with a's. Okay? So, something to note is that the epsilon delta definition of a limit doesn't actually help you calculate the limit. I told you here that prove that the limit is 6. So this is why we also, when we talk about limits, we start by saying, well, how do we find these before actually telling you the definition? because just having the definition doesn't help you find the limits anyway. So you need to be able to calculate with something. So that's why I gave you that really vague definition to start with. Now we have a definition that once you know what the limit is, you can actually prove it using this epsilon delta technique. Okay. So the definition doesn't actually help us to calculate the limits. It just helps us to show that the limit we found is right. You still need to be able to use graphs and numerical tables, and you need to be able to find limits analytically, which we're going to do today. Okay. So one last thing, delta in this case could have been anything. Usually delta is going to depend on what epsilon is, which intuitively makes sense. If I have to make f of x really, really close to some number L, well, how close I pick x to be should depend on how small that band is above. So delta is usually going to depend on what epsilon is. This was a very special case that it didn't depend on epsilon. So to see in the case where delta does depend on epsilon, let's look at this example. Use the epsilon delta definition of the limit to show that the limit as x approaches 3 of 4x minus 7 is equal to 5. We don't take delta ever to be 0, by the way. Delta is always strictly positive, and epsilon is also always strictly positive. Okay. All right, so again, this is an epsilon delta proof. So what should be the first 3 things that you write? Really like the first 6 words. Perfect. Let epsilon, if you want to call it an E, that's fine. I don't care. Let epsilon be greater than 0. Okay. Again, this is math speak for Chase walks into the room and shouts, epsilon equals 0.001. Okay, it's your job now to find delta. Okay, so we have epsilon is greater than 0. All right, so then we want to show, again, that we can find delta so that if 0 is less than x minus 3 is less than delta, the x minus 3 an absolute value, then the absolute value of f of x here is 4 times x minus 7. So f of x minus 5 is less than epsilon. So again, this guy here is f of x. All right, so then the epsilon delta proofs, they always work backwards. You work backwards from here to find what delta has to be so that I get this. Okay, so it's going to seem a little circular in that sense, but that's how we have to go about these problems. So if I actually plug in f of x on the left of this, then I want to show that the absolute value of 4x minus 7 minus 5 is less than epsilon. I want to show I can find a delta so that I get this inequality. Well, what does that left-hand side simplify to? Yeah, exactly. It's just an arithmetic problem, right? So that's the same thing as absolute value of 4x minus 12 less than epsilon. If I can show this for a given delta, then I'm good. Okay, but what can I do on the left-hand side there now? What do each of those terms have in common?
Divide by 4.
Perfect. I can pull out a 4. So the left-hand side here, well, this is 4 times, and 4 in absolute value is 4, so I'm not going to put in absolute values, but 4 times x minus 3, right? less than epsilon. Okay, and then who sees what we're going to do next? Yeah, I can solve this. I have here absolute value of x minus 3, which is what we're trying to find, right? We're trying to find how close does x need to be to 3 so that I get that first inequality I wrote. Well, I work backwards from the first inequality I wrote to get here, and this tells me that absolute value of x minus 3, divide both sides by 4, this is less than epsilon over 4, right? So what do I need to take delta to be? Delta needs to be, well, if I started here, then I found out that the absolute value of x minus 3 needs to be less than epsilon over 4. But I could have started here, right, and gone backwards each step. I could have started here, multiplied by 4 to get that, and then multiplied by, or distributed to get that. And then I could have made minus 12, minus 7, minus 5, like that, right? So, I mean, even though I worked backwards, now that I have that the absolute value of x minus 3 is less than epsilon over 4, I can go backwards from my backwards work and say that if absolute value of x minus 3 is less than delta, where I'm taking delta to be epsilon over 4. Delta equals epsilon over 4. Okay. Then, again, now just start from here and work backwards. Then we get what we want. We get the absolute value of 4x minus 7 minus 5 is less than epsilon, which is exactly what we wanted. Okay. So if you're concerned about the fact that there's no 0 here, I mean, you can put that 0 in. That doesn't really matter in this case. We would still end up with the line that we care about. Okay. Are there any questions on this? So is it clear to everybody that delta is epsilon over 4, that delta we want to take to be epsilon over 4? And when we do that, that guarantees that f of x minus L is less than epsilon. All right, so this type of problem, this linear limit here is the only type of limit that I expect you to be able to do on an exam with the epsilon delta definition. So knowing that, does anybody have any questions? Let's see your chat. Ah, that's an excellent question. Someone asked, what's the big picture? So let's look at, if I look at the line, we were looking at y equals, I forget what the function was. It was 4x minus 7. We're looking at y equals 4x minus 7, right? And we were looking at the limit as x approaches 2. Can I draw on this? No, I can't. I probably can. No, I don't know. But we're looking at the limit as x approaches 2. So I take the, I'm just going to draw it on Desmos. I look at the graph, y equals 4x minus 7, 1, 2, 3, 4, 5, 6, 7, and then up 1, 2, 3, 1, 2, 3, 4 over 1. So here's 4x minus 7, and 2, 3, 4, 5. I take a little bit of epsilon. I take a tiny little band around the y value, y equals 5, right? The whole idea is like, I start with that. I start with the fact that I want y to be between these two values. So the whole idea is, well, what x values do I have to be between down here? at x equals 2. So the whole point is to try and find this little band, how wide that little band has to be. And that little band has to be the epsilon over 4. That's what we're finding there. Okay. I'll draw a better graph and upload it after class, just so everybody knows. Okay, so the key idea here is that epsilon delta proofs work backwards. Oh, one more question. Again, epsilon and delta can't be equal to 0. So the key proof here, the key idea here is that epsilon delta proofs work backwards. You start with what you want. You start with the absolute value of f of x minus L is less than epsilon. You start from there and work back to, okay, what does x minus a need to be? And it will normally be hiding somehow in that absolute value of f of x minus L is less than epsilon. Sometimes you need to do a lot more work, but with linear functions, as you saw, most of the time it's just, not most of the time, every single time it's just going to be factor out the slope essentially after you take that subtraction. And that's why I expect you to be able to do it on an exam. Okay, all right. That's exactly what I just said, sorry. All right, so before we get into calculating limits analytically, there's a few basic rules that you need to know, and we can build up everything else that we know from these rules. And so hopefully they all seem pretty natural. If they don't, let me know. So in what follows, a is just going to be the limit as x approaches a. That's going to be some finite real number. And L and M are going to be finite real numbers as well. And so is C, okay? So, and L and M, L is the limit as x approaches a of f of x, and M is the limit as x approaches a of g of x. Okay, so here's the big table that you're going to need to know. Again, it should all seem pretty natural, I hope. So we proved specific cases of these two right there, but hopefully you can see that like what we did, you can just replace all the specific numbers I had with just general constants, and you would still end up with the same proof. So the first one says that the limit of a constant is a constant. The second one says that the limit as x approaches a of x is just a. The third one says that the limit of a sum is the sum of the limits. Okay? Hopefully that one seems pretty natural. And really all of these, the limit of a product is the product of the limits. The limit of a quotient is the quotient of the limits. And the limit of a power is the power of the limit, okay? And here, oh, oops, I used different letters here. Sorry, this should be an M because that's an M. And that M, that little m there could be, it doesn't just have to be an integer. That could be any power. It could be a square root. It could be anything, okay? So using all these rules, we can find limits of essentially every function that we care about. Polynomials, rational functions, you know, again, square roots, cube roots, so on. And in a second, I'll show you a rule that will help you calculate the limit for any algebraic function, okay? So are there any questions about any of these? Okay, well, so a proof for I'm going to show you a proof for the sum and difference rule. If anyone gets lost, just shout at me, and I'll stop and go back. So we want to show that if the limit as x approaches a of f of x is L, and the limit as x approaches a of g of x is M, then the limit as x approaches a of f of x plus g of x is L plus M. Okay, so first of all, we're going to write down what we know. We know that this first line here means that first I need to say let epsilon be greater than 0, because that's how all of these proofs start. So that first little bit of information tells us that I can find there is, I'm going to call it a delta 1 greater than 0, so that 0 less than x minus a less than delta 1 means that the absolute value of f of x minus L is less than epsilon over 2. And the over 2 is going to be important later. Okay? But I'm allowed to do that because if someone had come in and said, instead of epsilon, find f of x, find delta so that f of x is within epsilon of L, they could have come in and said epsilon over 2, and I still could have found a delta. Okay, so you're allowed to. That's why I'm allowed to say this. Is that clear to everybody? Hopefully, everything. The epsilon over 2 might be a little weird, but is everything else clear? That I'm just writing out the definition of the limit as x approaches a of f of x is L, which we're taking for granted. Okay, so same way we can find, because the limit as x approaches a of g of x is m, I can do the exact same thing. It might be a different delta though. Does that make sense? G of x could be something totally different from f of x. So there is also delta 2 greater than 0, so that, again, 0 less than x minus a in absolute value less than delta 2 means that the absolute value of g of x minus m is also less than epsilon over 2. Any questions on that? Okay, so then the one other thing that we're going to need is the triangle inequality. I'll show you guys where that comes into play in a second. Prof, there should be an O there. But, so now we want to show that we can find delta so that f of x plus g of x, and then that minus L plus m. I want to show that if I take x close enough to a, that f of x plus g of x will be close enough to L plus m. Okay, but now I'm just going to simplify what's inside there. On the left, we have, I can rearrange a little bit. This is the absolute value of f of x minus L plus g of x minus m. I want to show that this is true, right? Okay, and now I'm going to use the triangle inequality. Does everybody know? If you don't know the triangle inequality, that's fine. Does anybody know the triangle inequality? So the triangle inequality just says, and it's based on the fact that if you draw a triangle, and this side has a length of A, and this side has a length of B, then this side has to be, if you look at, I need absolute value of A plus B is less than or equal to, A and B are positive, so absolute. This side is less than or equal to always the sum of those two lengths. Does everybody remember that fact from triangles? That if you take one side and you add the side lengths of the other two, that the one side has to be less than. Okay, that's all the triangle inequality is. And now you just apply it to this thing, pretending that it's a length of a triangle, essentially. Okay, so let me erase this. Oh, oops, erase. So then I apply the triangle inequality. The left-hand side we have, this is less than or equal to f of x minus L plus absolute value of g of x minus m. And now if x minus a is less than delta 1 and delta 2, then each of these are smaller than epsilon over 2, right? That's what I started the proof with. If I said here, if x minus a is less than delta 1, then f of x minus L is less than epsilon over 2. And same way, if if x minus a is less than delta 2, then g of x minus m is less than epsilon over 2. So if f of x, or sorry, if x minus a is less than delta 1 and delta 2, and it's positive, then that tells us that this is less than epsilon over 2 plus epsilon over 2, which is indeed epsilon. Okay? I don't expect you to be able to reproduce this proof, because there's a few technicalities there. I'm just showing you that, and I can show you for the others, that they're true, which is important. Truth is important, okay? So, are there any questions about anything I did here, though, for showing that the limit of a sum is the sum of the limits?
Where did you get the x or the epsilon divided by 2 from the beginning? Like how'd you get it divided?
Yeah, excellent question. So again, we start off with let epsilon be greater than 0. And then for a second, I pretend that someone had said epsilon over 2. Because if I had just here said f of x minus L is less than epsilon, if I had said here, g of x minus m is less than epsilon, then here I would have gotten a 2 epsilon, right? I would have gotten less than epsilon plus epsilon, which is, again, the fact that I can make it smaller than 2 epsilon is still fine. But to make the proof cleaner, here, f of x minus, I know that the limit as x approaches a of f of x is L. So if I take an epsilon, well then it could have just as well been epsilon over 2, and I could still find a delta. So that's all that is. And it comes from me working out the proof beforehand. Okay, and I know that's not a very satisfying answer, but that is the answer of where that epsilon over 2 comes from instead of just epsilon. Does that maybe help a little bit, hopefully? I hope so. Okay, so on exams, again, I only want you to be able to use the epsilon delta definition of a limit to prove limits for linear functions, which is f of x equals mx plus b. And in addition to that, I only expect you to use it when I ask you to use it. If I don't ask you to use the epsilon delta definition, then don't. It's way harder to use that than to essentially plug in the limits that you know. Okay, so don't use the epsilon delta definition unless you're explicitly asked to. Okay. So yeah, unless I ask you to, you're just going to use the things we're going to learn today and tomorrow to evaluate these limits. Okay. All right, we got a question in the chat. Hold on 1 second. So for limits, again, you're trying to find the delta so that x minus a, if x is within delta of a, then f of x is within epsilon of L. So I'm not trying to find an x or a y per se. I'm trying to find delta to restrict x. Okay, so let's use the table that I wrote down to evaluate some more complicated limits, okay? So we're going to apply the rules in the table to find the limit as x approaches -2 of x cubed minus 2x squared plus 15. All right, so you'll have all the tools that you need to do this now, because first of all, this is a sum, right? So what's the first thing that you should do when you get this limit? Yeah, you should, instead of trying to take the limit of the whole thing, you should break it into its pieces, right? You should break this into the limit as x approaches minus 2 of x cubed minus, or I mean, yeah, I'll write plus the limit as x approaches minus 2 of minus 2x squared. And then plus the limit as x approaches minus 2 of 15. Everybody clear where I got that? I just broke the, again, the limit of the sum into the sum of the limits. Okay, what rule are we going to use on this first part here? Yeah, this is just the limit of a power. And we remember that the limit, we know that the limit as x approaches negative 2 just of x is, you just plug in the limit value, right? The guy in the bottom. You just plug in negative 2. So then if I'm taking this, well, I just take the right-hand side to the 3, right? Does that make sense to everybody? So this first bit, I'm going to get negative 2 cubed, which is negative 8, right? Plus. All right, this guy, again, I mean, we have technically a product of minus 2 and x squared. So the limit of a product is the product of limits. The limit as x approaches minus 2 just of minus 2 of that first part is negative 2. And then what's the limit as x approaches minus 2 of x squared? Just 4, yeah, you're just plugging it in essentially, right? For the same reason that the limit as x approaches minus 2 of x cubed is negative 2 cubed. Here I'm going to get the limit as x approaches negative 2 of x squared is minus 2 squared is positive 4. Okay, and then what's the limit as x approaches negative 2 of 15? Yeah, just 15, exactly. So then, do I have extra space? Yeah. So then we got that the limit as x approaches minus 2 of x cubed minus 2x squared plus 15. Well, we got that that was minus 8, and then minus 2 times 4, so minus another 8, and then plus 15. And that gets us negative 16 plus 15, which is minus 1. Okay. Any questions on that? So this example illustrates something that you should know. If you're looking at the limit as x approaches anything of a polynomial, hopefully you see that you can just plug in. You use the same rules, you break it down the same way, and every time if you're looking at the limit as x approaches some value of a polynomial, just plug in whatever a is for a polynomial. Okay? Other times you'll have to do more work, but for polynomials, you can just plug it in. And we're going to see on Thursday, we're going to have a special name for functions like that. But for right now, I'm just going to tell you polynomials, just plug in the value. All right, so let's look at this limit. Find if it exists the limit as x approaches 2 of x squared minus 4 over x minus 2. So now if we just try to plug in x equals 2 here, like last time we could just plug in x equals negative 2 and it was fine. What happens here? Yeah, we get 0 over 0, which tells us nothing. That doesn't tell us anything. So we need to do a little more work here. Because the rule with division, I had a little caveat that said the bottom can't be 0 to use that rule. So who knows what I'm going to do? Perfect. The top, x squared minus 4, that factors very nicely into x. Well, who can tell me what it factors into? Yeah. Perfect. X plus 2, x minus 2. And then divide this by x minus 2. Okay. Hopefully everybody remembers a squared minus b squared. That factors as a plus b times a minus b. And that's all we use there for the top. Okay, what can I do next?
Cancel out the x minus 2.
Exactly. We cancel the factor of x minus 2 from the top and bottom. And we can do that, again, because we're looking at the limit. So I don't care what actually happens at 2. So I don't have to worry about canceling out zeros from the top and bottom because this is a limit, okay? And so then this just becomes the limit as x approaches 2 of x plus 2. Okay, and then what is that? Yeah, that's just 4. Now this, after I did a little bit of work, this is really a polynomial hiding, right? It is a polynomial in disguise, except for at one point, except for at the point x equals 2. But again, I don't really care what happens at that point. I care what happens close to that point. So you're allowed to just evaluate this limit, and I would evaluate this limit just by plugging in 2, and I get 4. Okay. Are there any questions about that? Very good. Okay, so with just one more theorem, we'll be able to calculate almost every single limit that's thrown at you. I mean, we'll need to learn a few techniques to make functions look nice enough to use these theorems, but you'll be able to calculate almost any limit I throw at you. So the following theorem will allow us to do that. If we suppose that the limit as x approaches a of g of x is L, and then the limit as x approaches L, so that's different. X is approaching L for f of x. If that equals f of L, then the limit as x approaches a of f of g of x is just f of L. Okay. Any questions there? I'm going to tell you, this looks a little more complicated than it actually is in practice. This is really just saying if the limit of the outside guy exists, just try plugging in a to the whole thing, right? Because this is really f of the limit as x approaches a of g of x, right? And so that's all this is saying, is essentially try plugging in a first. Okay. All right, so find, if it exists, the limit as x approaches the square root of 3 of the square root of 1 plus x squared. All right, so I'm going to walk through this explicitly using that theorem from before. Here we have f of x is just the square root of x. That's our outside function. And our inside function, the inside function that I'm plugging in, g of x, is what?
One plus x squared.
Perfect, 1 plus x squared. Does everybody see then that if I define f of x to be square root of x, and g of x to be 1 plus x squared, then when I take f of g of x, I get the square root of 1 plus x squared. Okay, so then looking at that theorem from before, first I need to look at what is the limit as x approaches the square root of 3 of 1 plus x squared. Well, what is that? What's the limit as x approaches the square root of 3 of just 1? 1, exactly. And then what's the limit as x approaches the square root of 3 of x squared? 3. Yeah, I take the square root and I square it. I'm just left with what's underneath. So I get 4. Okay, and then I also need to look at so this is L. Then I need to look at the limit as x approaches L from the last theorem. So the limit as x approaches 4 of f of x. Oops. And f of x is just the square root of x, right? So the limit as x approaches 4 of the square root of x. But the square root of x, that's just x to a power. That's just x to the 1/2. And so we have a rule for evaluating this, right? And so what is the limit as x approaches 4 of x to the 1/2? I think you said 2, right? Someone said 2. Yes, it's 2. You just plug in 4. We get the square root of 4, and that's 2. Okay? And so that theorem that I wrote down before says that this is just 2. And again, that theorem essentially says try plugging in this value. If it's a function defined, if it's not clearly like a function that's trying to trick you, most of the time you can just try to plug in the value. Okay. Any questions on that? Any questions from chat? Yeah, so someone said, why don't we just plug in square root of 3 from the start? That's exactly what you should do in the future. I was just showing you explicitly, step by step, what this theorem, what it looks like applied. But really, it's just plug in the square root of 3. Okay. Okay, so that was extra space. One more example, and then, yeah, one more example. Let f of x be 3x squared minus 6x. Find if it exists the following limit. The limit is x approaches 2 of f of x minus f of 2 over x minus 2. Okay, so I'm going to plug in f of x and f of 2. So the limit as x approaches 2 of f of x, well, that's just 3x squared minus 6x, minus f of 2. What is f of 2? Well, I'm going to get 3 times 4. Oops, 3 times 4 minus 6 times 2. And so that's going to give me 0, right? 12 minus 12 is 0. So that's just going to go away, 0 over x minus 2. All right, so if I rewrite this a little bit, this is the limit as x approaches 2 of 3x squared minus 6x, this over x minus 2. And then this is something that's going to happen a lot. What do we do next with the top? I factor it. Anytime you have a polynomial over another polynomial, which is known as a rational function, and you're looking at a limit like this, almost always you're going to try and factor either the top or the bottom, or maybe both, and try and get something to cancel if you're getting something that looks like 0 over 0. Because if I just plug in 2, I get 0 over 0, right? So I need to factor the top. What does the top look like when I factor it? Perfect. 3x, I factor out a 3x because each of these terms have a 3x in common, right? And then when I do that, I'm left with an x here and then a 2 here, x minus 2. All right, and then what happens? Beautiful. The x minus 2's cancel, and I'm left with the limit as x approaches 2 of 3x. And what is that? Perfect. That is just 6. Now we can just plug it in, right? And we get 6. Any questions on this example? So that idea of factoring the top and bottom, you're going to use that idea a ton. It comes up on the homework a few times that I have assigned, by the way, there's homework assigned. You won't be able to do all of it yet because there's some from later sections, but you'll definitely be able to do some of it now. So check Canvas for the homework. All the problems are from Calculus of a Single Variable by Larson and Edwards. If we don't have any other questions, then maybe try and think about how you would do this limit for tomorrow. This one's a little different. This one I can't really factor because I've got a square root happening. So think on what you might try and do here to evaluate this limit. Okay, if there's no other questions, everybody can feel free to wipe down your desk and then head out. If you do have questions, you can stick around and ask. I hope everybody at home followed this lecture.
Thank you.
Thank you.
Thank you.
Thanks.
Mhm.